Welcome to this deep dive. Today, we're focusing on a really useful tool, multivariate analysis of variance. You'll hear it called MANOVA.
hmm
Our mission basically is to give you a quick handle on what it does and, when you should think about using it in your own analysis.
Exactly. Think of it as a way to see the bigger picture, how different factors connect when you're measuring more than one thing, connections you might totally miss otherwise.
Okay, let's dive in then. What's the core goal of MANOVA? And maybe how is it different from ANOVA, which more people probably know?
Right. So the main thing MANOVA does is look at how your independent variables, the things you manipulate or compare, affect two or more dependent variables, like simultaneously.
Two or more.
Yeah, that's the key. ANOVA, it just handles one dependent variable. So, ANOVA might see how study method affects just test scores,
Mm-hmm.
but MANOVA could look at how that same study method impacts both test scores and, say, student anxiety levels together.
Got it. So it handles multiple outcomes in one go. Why do that instead of just running two separate ANOVAs, one for scores, one for anxiety?
Ah, good question. Two big reasons. First, if you run lots and lots of separate tests, your chance of getting a false positive finding something significant just by luck goes way up.
The type I error problem.
Exactly. MANOVA keeps that overall error rate under control. But maybe more importantly, it can spot relationships between those dependent variables.
Oh, so.
Well, maybe a teaching method improves scores but increases anxiety. A separate ANOVA for each wouldn't show you that combined pattern. MANOVA looks at them jointly, so it can pick up on that kind of multivariate effect.
Okay, that makes sense. That's pretty powerful. But like most task techniques, there must be assumptions, right? What do we need to check in our data?
Yeah, definitely. The two main ones are multivariate normality and homogeneity of covariance matrices. Bit of mouthful, I know.
Yeah. What's the gist?
Multivariate normality basically means your dependent variables, like their combinations, should follow a normal-ish distribution within each group you're comparing.
Okay.
And homogeneity of covariance means the way your dependent variables spread out and relate to each other should be, well, pretty similar across all your groups. You'd use statistical tests, look at plots, standard procedure in software.
Right. So once you've checked those, how does MANOVA actually tell you if there's a significant effect overall? I've heard of Wilks Lambda.
Wilks Lambda, yeah, that's a really common one. You can sort of think of it as representing the variance in the dependent variables that's not explained by your independent variable groups.
So smaller is better.
Smaller means more variance is explained, yeah.
Yeah.
A small, statistically significant Wilks Lambda suggests your independent variables are having a real impact across that whole set of dependent variables.
So it really treats those outcomes as a system, not just individual scores.
Precisely. It considers their correlations, how they move together when figuring out if the groups are different.
Are there times MANOVA isn't the best choice? Maybe issues with sample size?
Oh, definitely. MANOVA can need fairly large samples, especially if you have quite a few dependent variables. With small samples, it might lack the power to detect effects that are actually there. It gets a bit shaky.
Okay. And what about Pillai's trace? I sometimes see that reported too.
Right, Pillai's trace. It's another key test statistic. Like Wilks, some argue it's a bit more robust, especially if your data, bends the rules on those assumptions a little, or if sample sizes are on the smaller side. Generally, a larger Pillai's trace indicates a stronger overall effect.
And if the test is significant, sometimes you see a multivariate interaction effect. What's that telling us?
Ah, an interaction. That means the effect of one independent variable on your set of outcomes depends on the level of another independent variable.
Perfect.
Maybe teaching method A improves scores and reduces anxiety for beginners, but for advanced students, it only improves scores and doesn't touch anxiety levels. The effect of teaching method depends on the student level.
Got it. Complex stuff. One last term. Discriminant functions. What role do they play?
Okay, so if your overall MANOVA is significant, let's say Wilks' lambda shows a difference between groups. Discriminant functions are follow-up analyses. They help you figure out which specific dependent variables are most responsible for separating those groups.
So they pinpoint the key outcomes driving the difference.
Exactly. They show the combination of dependent variables that best distinguishes the groups.
Okay, let's try to wrap this up.
Yeah.
The big picture is MANOVA is your go-to when you've got multiple outcome measures and want to see how some factor influences them together. It helps control error rates compared to multiple ANOVA days and can reveal those hidden multivariate patterns.
Hmm.
But you need to check assumptions like multivariate normality and homogeneity of covariance, and be mindful of having enough data, enough sample size.
Yep.
Stats like Wilks Lambda or Pillai's trace give you the overall significance, and things like discriminant functions can help you unpack which outcomes are driving any effects found.
You've got it. It provides a richer, more holistic view than looking at variables one by one.
So here's something to think about for you, the listener. Consider a research question, or maybe a data set you're familiar with. How might applying MANOVA give you a deeper insight than just looking at each outcome variable on its own? What new questions might that perspective raise for you?
Good thought to end on.
That's our deep dive for today. Thanks for joining us.